Hello, Prairie Trail students. We are going to continue looking at proportional relationships today, but we're going to get into what they look like when we graph them. That's going to extend our learning from lesson 1-4 where we just worked with the table of values. Before we do that though, I would like you to look at the launch, read each scenario, and decide whether you think that would meet the requirements to show a proportional relationship or not based on what you learned in lesson 1-4. Read each one and please do explain your reasoning for both, even though this one doesn't ask for it, and then later in the lesson you'll see if your hypothesis was correct or not. We will reveal in a moment with examples whether your hypotheses were right for the launch problems, but first let's talk about some vocabulary that we're going to be using as we make our graphic relationships today. So push pause on the video and copy these definitions since we all write at different paces, and once you have the definitions written down, come back and we'll label the grid together. Alright, the coordinate plane is the grid for graphing, which means the overall whole thing is our coordinate plane. I'm going to abbreviate right there as we label it. The origin is the center, this point 0, 0, where the two lines intersect. And you might want to point to that and say that that's the origin if your arrow didn't print very well. The ordered pair is this whole description of two numbers that tells where a point lands inside of the coordinate plane. The first number of that ordered pair, so in other words here the 1, that's our x-coordinate. And the second number, or the 2 in that example, is the y-coordinate. And the x-axis is horizontal. In case you don't remember what horizontal means, it means going left to right. And since the x-coordinate is first, it tells us to go left to right first. So right here, this is our x-axis. Since it is pointing, this arrow is pointing to this line right here, going across. And this arrow is pointing to this line that goes up and down, and that's what vertical means, up and down. So that's our y-axis. And since the y-coordinate is the second number, it means the second thing we do is go up and down. So for this example, 1, 2, start at the origin, go right 1 and up 2, and that's where you land at that point. Oops, I forgot I wanted to show you one more thing about some background information before we actually get into the example, and that's about writing equations. Please make sure to mark that so it's easy for you to find, because often I have students forget how to write their equations, and you want to be able to quickly find this section in your notes when you're looking up how to do it. So when you write the equations to represent the proportional relationships, the format is always y equals a blank times x. And that blank right there, so it's referencing this blank right here, is the unit rate for the relationship. And we've worked with unit rates already. Sometimes we see this called y equals kx, which means just some random number. Once you get into algebra, it'll be called y equals mx. But all that matters for us this year is that we have some number, so I'm going to just put it like a number right there, that's multiplied with x. So every equation is going to be y equals. Every equation is going to have a number times x, and we're not going to have any adding or subtracting or anything extra beyond that. Alright, so now let's get into our examples. Like I said, it's coming from that launch, the ones you already predicted, and we're going to practice representing the relationships in multiple forms. You're going to be given the word form, and from those words we're going to identify our variables, just like in science class when you have to identify the independent and dependent variables in a relationship. We're going to represent numbers in a table and then graph those numbers in ordered pairs in the graph, and then we're going to write the equation to represent all of it. So here we go. The variables here are number 1, where it says a touchdown is worth 6 points and is the total number of points proportional to the number of touchdown scores. So to find your variables, you want to just find the two things that are being compared in the problem. So is the number of points proportional to the number of touchdowns? So those are our variables. When you're making your table or your graph, you have to think about the order of which one would come first. Do we score points first and then get touchdowns, or do we score a touchdown and then get points? You may not be familiar with football, but hopefully you know that first you would do the touchdowns, so I'm going to abbreviate that with TD, and then you would earn points based on those touchdowns. It may seem obvious, but it is important for us to pay attention to whether we have that origin included. Remember that vocab word from the other side, the origin is right here, this point 0, 0. So we need to know, do we have the origin included in this? So in other words, if I score 0 touchdowns, how many points would the team have? That would still be 0. So yes, we do have the origin included. What about if I score 1 touchdown? Well, it tells me that every touchdown is 6 points, so I'm just going to put 6 right there. If I score 2 touchdowns, that means I scored 6, and then again I scored 6, so that is 12 points so far. Now this is not incorporating any extra points, anything like that. This is just how many points have you earned from touchdowns. And then after 3 touchdowns, you've earned 6 points, and 6 points again, and 6 points again, so you have earned 18 points. We are going to turn these into the points on the graph by recognizing the ordered pairs that they are. So a 1 before a 6 is like the ordered pair 1, 6. A 2 before the 12 is 2, 12. And a 3 before the 18 is 3, 18. So let's graph those points over here. The origin we already have right here. 1, 6 means right 1 up 6. Now, luckily for you, we see that we already counted by intervals of 6 on the y-axis, so I do not actually count up 6 spaces. I just go up to the level of the number 6 right there. And then over to 2 and up to the value of 12, which is the second line up, and 318. So this was a nice graph that had nice intervals that worked well with us. That will not always luck out that much. Just like we had to be sure to label the columns with the variable names on the table, we also need to be sure to label the axes and put a title on our graph. So I might call this touchdown points or scoring summary or something like that, make up an overall title. And the X is what always comes first. So we have our number of touchdowns here. And then the y-axis is the one that always comes second. So first we get touchdowns, then we score points. So there's our graph all set up. And one thing to notice is that from the origin, it does have a straight line that would connect all the points, and an arrow shows that I could keep going and going and going if I wanted. Based on what you learned in lesson 1.4, you know that this table right here is proportional because all of these numbers would divide out to be the same. 6 divided by 1 is 6, 12 divided by 2 is 6, and 18 divided by 3 is 6. So on all of them, the points divided by the touchdowns are 6. So that means it is proportional. Did you get that right on the launch? Did you realize that they would stay consistent and related to each other? The way you can look over here on the graph and see that, without having to do any dividing, you can look at the graph and know that it is proportional by looking at 2 things. One is that it goes through the origin, and 2 is that it is linear. And that's actually another vocab, but it wasn't in our graphing vocab because it's something different. But the word linear, if you look at it closely, you see that it has that word line in it. So linear means it makes a straight line. It doesn't curve, it doesn't bend, or anything like that. So if you look at the graph of the relationship and you see that it's linear and you see that it goes through the origin, then you know automatically that it is proportional. To wrap this up, we want to talk about how to represent proportional relationships. We said that every single time you do a proportional relationship, it's going to be y equals a number times x. So in this case, I'm going to start with that since I know I have to. I'm going to start with y equals, I'm going to go ahead and give myself a blank times x. This is what I would highly recommend you do while you're learning to write these equations, so you remember what to fill in right there. So now what number will I fill in? Well, I can look at my points and see to get my y coordinate, every time what did I have to do to the x coordinate? So 1 times 6 is what made 6. 2 times 6 is what made 12. 3 times 6 is what made 18. If you had already done your dividing to find whether it was proportional or not, then you probably already had that number, as long as you remember to do the y divided by the x, keeping it in that order, not the order of the ordered pairs. So here, I know that the relationship was y equals 6 times the x, and that would be my relationship. Okay, the second example was about an outdoor swimming pool that cost $8 per day to visit during the summer. And also there's a $24 yearly registration fee, or maybe like a membership fee or something like that to belong to this pool or to be able to attend it. So we want to know, is the total cost proportional to the number of days that were visited? Since those are the 2 things that are being asked about in a relationship, I know that those are my variables, total cost and the number of days or the number of visits. So when I'm filling out my table, I have to decide, well, what do I do first? Do I first calculate my total cost and then I'm given a total amount of days I can go? Or do I first just go and then I figure out my total cost? And that would be the correct order. First, I'm going to actually go swimming at the pool. And then after I know how many days I actually went in the summer, then I can figure out what my total cost was. So remember, we're always going to check first with our, see if we have the origin included. In this case, if I never end up going swimming at all, I actually have already paid a $24 membership fee or registration fee to be given the option to go. So that means my graph is not going to start at the origin. If I come over here and graph that, from 0 go up to where the 24 is, then my point would land right here. So right away, I know that my graph did not hit the origin, so that's not looking good for me for its being proportional. If I go one time to the pool, then I did that $24 registration fee plus an extra $8, so I paid a total cost of $32. If I go twice, I had to pay the extra $8 again, so that would be $40. And if I go 3 times, then it's another $8 again, so that's $48. Turning all those into coordinates, right here, I know this is like the point 0, 24. This is 1, 32, 2, 40, and 3, 48. So I can find that on my graph by going over 1, up to the 32, over 2, up to the 40, and you keep doing it just like that for each one. Again, we pre-labeled these for you because we knew that we would be using intervals of $8 a day. If you have a blank graph that you have to make on your own, look for hints like that in the description. Like if we know that's what it's going up by each time, then that's what you can choose to count by. But notice, just because my first number was a 24 did not mean I can start with a 24 down here or even here. Once you pick an interval to count by, you have to consistently count by that. So I counted by 8, so I had to start with 8, 16, 24, even though I didn't use those values. All right, my graph might look good to you, but remember, it is not complete until you have everything labeled. So this is going to be pool costs. I'm going to call as a title. You make some sort of title up to describe overall what's happening. The x-axis is what came first, so this was the number of days or number of visits to the pool. And the y-axis is what we're calculating based on that. That means this is my dependent variable because it depends on what I did first. And that is going to be total cost right there. And I see that my graph is in a straight line. However, I'm not actually going to connect them. And I just realized I did this wrong on the other graph as well because I was showing you what it meant to be in a straight line. So it is linear. They are in a straight line. But I only connect the spaces between the points if it's possible to have data between these values. But I'm not going to go swimming between 0 and 1 days. If I go to the pool, I go to the pool. I don't go half a time. Or I can't go like 1 3/10 time. So since I can't have possible answers between here, I'm not going to connect the space between there. So I'm just going to visually look right here that it is a straight line. It is linear, but it is not in the origin. So I check both things. Linear, check, it's good. But origin, no. Which means automatically that it is not proportional. It has to meet both for it to be true. On the graph, we could see that, on the table, we could see that as well. We could see that if I tried dividing 24 divided by 0, automatically that doesn't work because we can never divide anything by 0. 32 divided by 1 is 32. 40 divided by 2 is 20, and 48 divided by 3 is 16. So it does not consistently give me a unit rate, so it is not proportional. There's not one consistent unit rate, so it is not proportional. Before I go down to the equation, will you push pause, go back to the first graph, and erase the line right there since you weren't supposed to connect, since we can't earn points between 1 touchdown, 2 touchdown, 3 touchdown, like that, based on our counting by sixes. We could get extra points and field goals and stuff, but that's not what we are considering. All right, to wrap up with this equation, I'm going to go ahead and show you this because some of you are really good and have good inquisitive minds at wanting to look ahead at things. But I want to let you know that if it is not a proportional relationship, you do not have to do the equation because it's beyond what we have to learn in 7th grade. But some of you are good at thinking ahead, so I want you to know it's still going to be y equals something times x. But when we do that, since we did not have a unit rate here, there's not one thing that can just directly multiply this to this, and this to this, and this to this. So we're not going to be able to stop there. But I will let you know, in case you're curious of what it would look like, that it would be y equals 8x, since it's going 8 each time, but we would also have to add in that 24 in order to make it work. So 1 times 8 is 8, plus 24, that's where I get 32. 2 times 8 is 16, plus 24 is 40. 3 times 8 is 24, plus 24 is 48. It's because I had already prepaid something right here before I started going up. That's where that plus 24 comes in. But the reason why I still wanted to write and show you is so that you know if you ever see an equation that has extra information besides the multiplying, then you know right there, before you even see the table or the graph, you know that it is not proportional, because every proportional relationship will just be y equals a number times x. Okay, you've seen all your examples. Now stop and think through, do you know how to test if it's proportional in all these 3 different ways? Push pause on the video, write down what you know, and then come and check yourself, see how you did. Okay, lesson 1.4 taught us that from a table of values, we can divide all the numbers out, and we should look for a consistent unit rate. Today we talked about when you graph it, you need 2 requirements, linear and through the origin. And since both are important, I'm going to circle that to make sure you look for both. And for the equation, it should be y equals that unit rate number times x, and nothing else should be added or subtracted or included in the equation. That's it. We'll continue practicing proportional relationships in class.